So this is going to be the third lesson of the second chapter, and this is going to be basically about how to write and analyze a histogram. So there's actually going to be a lot of, again, informational stuff here. There's not going to be a lot of calculations again. It's going to be, again, excuse me, a little bit hiccup, more instructional than sort of computation-wise. So let's just get right into it. It probably should be a fairly short one too, because, like I said, it's very a focused lesson. So first off, the big thing about histograms. Histograms are basically bar graphs with no gaps to them. So over here on the left, you have a bar graph. Over here on the right, you have a histogram. Bar graphs deals with categories usually. Histograms deal with number ranges or frequency distributions, like we said before. And again, bar graphs have space between the bars. Histograms have no gaps between them, just to show the distribution a little bit better, which we'll get into a little bit later here. So just again, let you know the key difference between a bar graph and a histogram because they are kind of similar. So a histogram is basically a bar graph which has bars together. The horizontal or the x-axis represents the data values for the classes. So that's the class ranges there. And the vertical axis or the y-axis represents the frequency of each class. So y-axis is the frequency, x-axis is the class limits, kind of, or actually the class boundaries, which we'll get into in a second. And again, this can be done with a normal frequency table. It can be done with a percent or relative frequency table or a cumulative frequency table. So any type of frequency table you have, you can do a histogram with. Cumulative is kind of weird because remember, cumulative is that rolling sum, so it's a little bit harder to deal with cumulative, but with some creative adjustments, you can make it work. Um, so let's go ahead and take some look at some of the stuff here. So how do we make it? Well, first we need a frequency distribution, obviously. And then we're going to plot the bottom line. So the bottom line is where people get most confused, the x-axis. You do not use the class limits for the boundaries of your bottom line. You use the class boundaries, which are those invisible middle points, or you use the class midpoints for your bar markings. So what that means here is that if your class, let's say your first class, let me do it in black here just to make it show a little better. So let's say your first class was 5 to 10, and your next class was 11 to 16. That means on a histogram, you wouldn't put 5 to 10. You wouldn't do that. What you would do is you would put the class boundaries, which it looks here, would either be 4.5 to 10.5. Again, why 10.5? Well, because if this ends at 10 and this starts at 11, that means the invisible boundary here is 10.5. Because if I just put a 10 here, then I don't know whether that 10 belongs to this bar here or whether it's going to belong to this bar here if I put a 10 there. So I'm going to use the class boundaries. That way we know the boundaries are there simply as a buffer, and we know that to the left of the boundary is where the 10 goes, and to the right of the boundary is where the 11 goes. So that's why you do not want to use the exact limits of the class. You want to use the class boundaries to help you out there. That will give you a nice spacing for your bars there. And notice that we didn't really know the class before this, so I used 4.5 just because that seemed to be the pattern. 10, 10.5, 11. Presumably this would be 16, 16.5, 17. So I just figured that I would go, if I went 10 to 10.5, I would go 5 back to 4.5. Although some people, if it's the very first class, they'll actually use the lowest number just for completeness sake. Let me adjust something here real quick, so hold on. So a little bit of mic issue there, sorry. So again, it's the class boundaries that split up your bars, not the class limits. Or sometimes you can even use the class midpoints. So if this was the case, the midpoint between 5 and 10 would be 7.5, right? So this would be 7.5 as the midpoint. So sometimes you'll see a histogram where you'll have your first bar like this, and instead of saying 4.5 and 10.5, it would say in the middle 7.5. And then the next bar, let's see here, that would be what, 13.5? So it'd be 13.5. So they would use the class midpoints instead, just to reduce the clutter. I really don't like that method because it just makes a little bit more work to understand what each bar represents. But for computer histograms, they usually have that as a default. And if you're just looking for the overall distribution or shape of the histogram, it doesn't really matter. But I much prefer the class boundary method just because it's easier for me to read and understand. But that's my own preference. So what do we get when we finally make a histogram? The main thing is we can tell the nature of the distribution, which is either normal, skewed, or what we call uniform. So normal, we talked about last time, normal is when the bars form roughly a bell curve, which is what we have down here. So we have lots of low bars on the ends, and in the middle of the histogram you have your high bars. So that would be a normal distribution when you have that nice bell curve shape. A skewed distribution is simply when the bars are stacked either to the left or the right. So if you have lots of low bars here, and then you have lots of high bars at the end, that would be a skewed distribution. And if you flip this to the high bars at the beginning and then it shoots down to low bars at the end, that'd also be skewed. So skewed is when you have a bunch of bars stacked to either the extreme left or the extreme right. If everything's about the same like this, so let's say you have a histogram and stuff is like this, where there's some differentiation, but for the most part, they're pretty much the same height. That's what we call a uniform distribution. So if there is no curve up or curve down or extreme hump to the left, then it's a uniform distribution. And again, the key here is that we have to use a data set that's sizable enough in order to get an accurate estimate. If we use a data set that's too small, then we don't really get a lot of information out of the histogram. So again, sample size is always as important. So let's take a look at one here. So this one's actually using the midpoint method, mainly because they don't really have classes. We have 1, 2, 3, 4, presumably like rolling a die, it looks like. So if we're rolling a die, the amount of times we got 1, the amount of times we got 2, the amount of times we got 3, and so on. So because there's really no boundaries here, they opted for the midpoint section. So the midpoint of 1 is just 1, the midpoint of 2 is just 2. So essentially your class width here is just 1. So it's not really much to go off of for class boundaries, so they just use the midpoint method. But this would be a nice spaced histogram. So you have the class midpoints down here, which is the classes themselves in this case. You have the frequencies on the left side, and then you have the bars all squished together. And this looks like it'd be a roughly normal distribution, because if I draw a curve out here, it looks to follow a rough bell curve. Again, it's pretty symmetric, so the extremes here are roughly the same as the extremes here. Not exactly, but they're about the same height. And the two middle bars are roughly the same height as well. So this looks to be like a roughly normal distribution where the middle numbers occur the most often and the extreme numbers occur lower than those in a somewhat similar fashion. But again, this would be an example of a completed histogram using the class midpoint method. Let's look at another one here. This is using the class boundary method, and from this we can actually get what the frequency table was to begin with, right? So this is the amount of scores for a certain stats test. So this is stats A being the class. So this is, I guess you'd say first class if you want to say first rather than class A. So the first stats class test scores on their last test came out to be this. And because, again, we can see here that this is 18.5 and 21.5. So that means that this bar right here doesn't represent 18.5 to 21.5. This bar in the middle represents 19 to 21.5. So 19 to 21. Because it's half a mark up from the low and half a mark back from the high. Because again, these are the boundaries. So this first class is 19 to 21. This next one here, 21.5 to 24.5, that would represent the class of 22 to 24. This would be the class, let's see, 24.5, 27.5. So this class would be 25 to 27, and this would be 28. Whoops, try that again. 28 to 30. So again, these are the boundaries of the table, not the actual class limits themselves. The class limits are the halfway marks that are contained inside those bars there. So you can kind of reconstruct the frequency table if you want to. And this is definitely a skew distribution. So if I try to draw a curve here, I definitely have a larger hump on the right than I do on the left. So this is a skew distribution. And luckily for this class, it's skewed to the right, which means that we have a higher than normal, we have a more than normal amount of high scores. I was trying to say that right there. So we have a more than normal amount of high scores because our data is skewed towards the high end rather than the low end, which is good for this class. That means more people than what we would expect are scoring higher than we thought they would, which again is never a bad thing. It doesn't say how many points this test is out of, so it's kind of hard to tell whether it's A, B, C, D, or F. But again, we know that the higher you score, more often the better you do. So. But again, these are boundaries, not class limits. The boundaries. So there are 3 people that scored between 19 and 21 points, 3 people that scored between 22 and 24 points, and so on and so forth. This is for the, we'll call, again, this is stats C. We'll call it the second stats class if you want, class second. Same idea. These are the boundaries of this class. This one had a little bit of an even spread here in terms of class boundaries. So this right here represents not 20 to 23. This represents 20.5 to 22.5. So the actual class here is 20.5 to 22.5, not 20 to 23. And then again, going down here is the same idea. So this is 23.5 to 25.5. Okay, so that's what these numbers here represent, are the boundaries, because between 22.5 and 23.5, right in the middle is 23. So I know that 23 actually isn't counted, but I know that the 22.5s fall into this first bar and the 23.5s fall into this second bar here. Because let's say my first class was 20 to 23 is equal to 3, and then 24 to 27 is equal to 5 or something like that. So if this is the case and I put a 23 here, well, on the histogram, I don't know if I'm counting the 23 over in this bar or whether I'm counting the 23 over in this bar. Now from the frequency table, I would know because the frequency table shows me that directly. But if I didn't have the frequency table like I don't here, then that would be very confusing as to know whether this bar contains the 23 or this bar contains the 23. But if I know that they're following standard statistical procedure, I would know that this 23 is the boundary and that this bar actually represents the boundary between these two numbers, and this bar represents the boundary between these two numbers. So again, it's very important to use the class boundaries, or if you want, the class midpoints, not the actual class limits. And this looks to be more of a normal distribution. Yes, it's not as symmetric as we'd like. Usually in a bell curve, it's nice and symmetric where the low and the high ends have roughly the same amount and the middle numbers have the highest amount. But for the most part, it looks to be a pretty decent bell shape here. Again, a little bit lower on this end than we usually expect, but not that big a deal if we're going for the overall assumption of it. And again, you could also have done this using the midpoints. So if this was your class, then instead of doing these down here, instead of doing these numbers, they could have done this, 21, and put that smack in the middle. Let's see, the midpoint here would be what, 24? I'm probably getting these midpoints slightly off here, but 24.5, right? And this would be 21.5 as the midpoint. So they could have used the class midpoints as just a single dash mark there instead of using the class boundaries as the ends of the bars there. But again, that's just a preference thing. Again, I prefer the boundary method just because it's easier for me to understand and read. So this is the graph of both of them combined. So if we combine stats first class and the second class of stats and combine their quiz scores, we get this. It says the average overall score was 25.24. Again, we don't know out of how much, assuming that nobody got an exact perfect, or sorry, assuming that somebody got 100%, because usually in every class there's that one person that gets at least 100%, right? We can safely say that assuming there's at least one person that got 100%, it looks like the class, the highest score was a 30.5 or a 31. Again, sometimes statisticians get lazy and the last boundary they make is the actual class limit rather than the class boundary. So this could be possible that somebody actually did score a 31 exactly. But again, that's just some ambiguity there. But if we put both classes together, this seems like it'd be a roughly skewed distribution. If it was a normal distribution, we expect this bar to be a little bit higher and closer to 13. Like if it was like right here, then if that was this bar here, that would be a roughly normal distribution. But as it looks like now, it seems like it's a little bit more skewed. Again, luckily it's skewed on the high end, or towards the high end, I should say. Because if I draw my curve here, and then we have a sharp uptick there and down there, and it looks like the hump is more towards the right side than it is to be towards the center, just by a slight amount. So this would be a skewed distribution here, we'd say, because of the fact that, again, the hump is more towards the right side than the left side. And again, these are not the limits, these are the boundaries. So these 4 right here, this 4 represents that there's 4 people that scored between 18.5 and 21.5. 0.1, it looks like, assuming that they're going by 0.5s here, which they might not be. I don't know. I made an assumption there just to make it easier, but that's what this 4 here represents. And again, these might seem like weird class limits, but you have to understand if you're taking all the test scores on a test and you're trying to make a equal distribution of classes there, you can get some weird numbers for class limits slash class boundaries. So even if they look weird, again, it's just the way that the data comes out to be nice and evenly spaced there. Um, so again, boundaries down here, not the class limits. Um, and that's about it. Like I said, this was a pretty short, sort of quick lesson there about how to read and write a histogram. I think there might be, no, that's it. Just to let you know, a uniform distribution, if I go back here, a uniform distribution, because we didn't see one of those, would look something like this. So if this is a uniform distribution, we would expect it to look something like this here. So this bar would be roughly, let's say, up here. This bar would be kind of like right here. This bar would be somewhat like right here, and this bar might be somewhat right here. This would be a uniform distribution if the bars were like this, because that's roughly like one even block there. So if all the bars are roughly the same height and you have kind of like a square or a rectangle almost in the middle, then that's what we call a uniform distribution where everything's occurring about at the same rate. Whereas again, skewed and normal have that hump either in the middle if it's normal, or to the left or to the right if it's skewed. So. That's it for this video. Once again, the key thing to take away from this, other than, again, most of the information, is the bottom numbers. The bottom numbers are either like this, where they use the class midpoints because they only have one limit in the class, or they're like these, come on, where you're using the class boundaries, not the class limits as your bar endings. So again, boundaries, not limits, because you want to make sure that they are fully aware as to what data is in each bar. I know exactly that this bar contains 19 to 21, 22 to 24, and so on and so forth. There's no ambiguity about where this 21.5 falls because 21.5 isn't actually part of the data. It's just used as a buffer zone to mark the end of one and the beginning of another class. So that's it for this video. Short, I know. Hopefully it helped you out. If you have any questions, like always, let me know. Otherwise, have a good day, night, evening, or whenever you're viewing this.